in the way of the success. So yeah, okay, so we are proud of them, to the Aztecs. Okay guys, so let's continue. So in the previous class, so if you remember, we had this fourth order system of spring and damper. Okay, spring springs and masses like this. Okay, and we derived everything together, and we saw that for y over x, I don't want to write like this, was a constant number, whatever it is, I don't care, and s, yes, you can't. Hold on. How about now? Okay. So in the previous class, we had this spring and masses. So we had we put that fourth order system plus the bs square plus c. That's right. And I showed you that we were missing some terms like as s cube and s, and we simulated that and we saw that we have instability at the end of the response. Remember? So today I'm gonna extend this problem, okay, by adding physical damper to that, like this. And to distinguish what's gonna happen to poles of the system. Remember that we have the right hand poles, that's right? So what I'm gonna do, I'm gonna have this damper here and spring, and this is the mass 1, M1, K1, C1, and I'm gonna keep this as K2 and M2 and K3. This is C2 damping coefficient. And what I'm gonna do, again, I'm gonna apply a force here like as F1 and a force here as F2. But look at previous case, if you let me, for simplicity of the teaching, I'm saying only there is F1, okay? So I want to just compare the denominators. This is fourth order system. Oops. What happened? Okay. Denominator, fourth order systems, right? So again, saying that here is x1, obviously, and here is x2. So sum of the forces from the dynamic course is mx double dot, Newton's second law. So what you're gonna have, then we're gonna go to MATLAB, okay? So we're gonna have m1 x double dot 1. So we cut from the system from here, cut the system from here, and cut the system from here. For m1, you have reaction force of, by assuming that x1 is greater than the x2, because the previous class is being stretched. So you're gonna have fs1 this way. You're gonna have fc1 this way is reacting. Here you're gonna have, it is being compressed because x1 is greater than x2. You're gonna have for this f spring 2. Okay, so what you're gonna have, f1 external force minus fs1, as you know, is k1 x1, is minus c1 x dot 1, you know, that the damper. Okay, and fs2 is minus k2, and like as previous class, x1 minus x2. Okay, So for the other mass, changing the color, we have exactly like as previous class, the same force in the opposite direction, Fs2, and is being stretched. You have Fs3 spring and Fc2 damper forces. So you're gonna have M2 x double dot 2 gonna be, there's no F, so you're gonna have minus K3 x2 minus C2 x dot 2, but the same but in the opposite direction, x2 x1 minus x2. So what I'm gonna find, I'm gonna find this I want to find x2 like as previous class over f1, this transfer function. Here we go. Why I'm doing it? Because eventually I'm going to teach you the Roche stability criteria. Not now, toward the end of the semester on April 20th, 25. Okay. So if you rewrite everything, you get m1 x dot double 1 plus c1 x dot 1 plus k1 plus k2 x1 minus k2 x2 is equal to f1. I transform this to this. Now we have additional here, damping term, physical damper. And m2 x dot double 2 plus c2 x dot 2 plus k2 plus k3 x2 minus k2 x1 is 0. So I'm going to play with a lot, okay? Because I'm going to go to MATLAB coding and I'm going to go to Simulink, both of them. What I'm going to do, I'm going to say Laplace to the both sides to compare with this, that we're missing these terms. Okay? By assuming that x1 at 0 is equal to x2 at time 0 equals to x dot 1 as 0 equals to x dot 2 as 0. Initial condition are zeros for Laplace. Yes. Here? No, it doesn't matter. So this is just force. This is external force. Okay? Here we have external force F1, but here we don't have external force. Okay? Initial condition doesn't matter to the initial to external force. That's independent. Okay? Okay. So can I go to next page? Yes. So what you're gonna have is m1 s square x1. I'm dropping this plus c1 s x1 plus k1 plus k2 in x1 minus k2 x2 gonna be f1 in S domain. S square, S, and the rest. Now the other one, m2 s square x2 plus c2 s x2 plus k2 plus k3 x2 minus k2 x1 is 0. What I'm gonna find? This transfer function, x1 over f. So it's enough that I find from this equation x2, implement here, right? Or f1, say. Okay. So from here, you know that the x2 can be written as m2s squared plus c2s plus k2 plus k3 equals to k2x1. So you get that x2 is k2x1 divided by m2s squared plus c2s plus k2 plus k3. What I'm gonna do, I'm gonna implement this here. So you know that you can factor out this x1 from here. So you're gonna have x1 gonna be m1s squared plus c1s plus k1 plus k2 minus, now I'm gonna put k2 squared x1, I'm just putting here, divided by m2 s squared plus c2s plus k2 plus k3 is equal to f1. Now we have that. I'm gonna remove this, and I'm gonna remove this because x1 is there. I'm gonna put it here. Here we go. Everybody agree? So your x1 gonna be this by this. I mean this. Let me say for simplicity, m1 is equal to m2 is equal to m. For simplicity, c1 equals to c2 is equal to c. k1 is equal to k2 is equal to k3 is equal to k, because we are deriving together. So this is gonna be m and k1. I'm gonna delete this, delete this, and delete this. So what we're gonna have is cs is gonna be 2k. This is gonna be k squared. CS is gonna be 2k. Everybody agree? Yes? Answer is yes. So it's gonna be this square, ms square plus cs plus 2k square minus k square divided by ms square plus cs plus 2k is equal to f1. Now this is square, so it's gonna be x1 gonna be m square s4 plus c square s square plus 4k square plus 2 of this in this 2m c s cube plus 2m, it's gonna be 4mk s square plus in this and this plus 4CKS. Let me double check. This is square, this is square, this is square. 2mcs cube 4mk. Let me write clearly. 4mk square plus 4cks. Now minus this k square divided by m square plus cs plus 2k is equal to f1. Guys, now look at here, all of you. Despite the previous case, when I add damper, you have S4, S cube that we were missing. Look at here, we were missing here. S square, S that we were missing. See, we were missing here. And also this have S square here. And the constant numbers. Okay. So if you are done, I will let, and I'm gonna simplify everything. Can I go ahead? Yeah. Okay. So x1 over f1 gonna be ms square plus cs plus 2k divided by m square s4 plus 2mc s cube, see, plus c square plus 4mk s square, bingo, plus 4ck plus 4ck and 4k square minus k square plus 3k square. Okay, guys. So for accuracy, let me double check with some drawing with you. Slide. Yes, just I'm double checking, okay? Just give me a second. Yeah, no worries. So it's going to be M4 squared to MC plus 4MK plus 4. Yes. And now, as you can see, we have all the terms. S4, S cube, S squared, S, and a constant number. Okay. Now I give some numbers. M is 1 kilogram. K is, for God's sake, 100. And the C is 5. So, x1 over f1 gonna be s squared plus 5s plus 200. First of all, how many zeros this system has? How many zeros? How many zeros this system has? 2. How many poles? How many poles? Huh? How many poles the system has? 4. Because it's fourth order system. Gonna be S4 plus 2MC. 2 by, it's going to 10 S cube plus C squared. 25 plus 400. 1 in 10, 400 plus 25, 400. 425 S squared plus 4CK. CK is 500 in the fourth, gonna be 2000 S. CK is 500 for 2000. Plus, this it's gonna be 10,000, 30,000. But what's the difference between this and this? Here we were missing these coefficients. That's why our system was crazy at the end of that. So now, you know what I'm gonna say again? I'm gonna say F1 is 1 over S. What's the input to the system, guys? Now you know it. What's the input to the system? Tell me. Which input to the system is 1 over S? Oh, what is that? Which system? Which input? It is impulse, step, ramp, parabolic. Which of them is this input? Is what? Step. Exactly. And I taught you when it comes up. Come on. Okay. So what I'm gonna do, I'm gonna define it because I'm gonna share with you. I'm gonna say num is fourth order system. So gonna be 0, 0. Okay. So 1, 5, 200. This is S4, S cube. Now 5. How much numbers? 5. 1, 5, 200. So 1, 5, 200. And then is, can you read the numbers for me in sequence? 1, 10. Can you read for me? 1, 10. Anyone? Can you read from your notes? 425. Here we go. So I'm gonna say figure 1. Step, as I taught you. Step what? Step num and then. Okay, and the greet. And I'm gonna put CLC clear all. Okay, X label is time second, Y label is X1 emitter. Okay, now I'm gonna say that ME430 fourth order system. Okay. Fourth order sys. Okay. Now if I run this, it's a stable system and it's underdamped. See guys? But for making sure that it's settling down, I'm gonna increase the time. Yes, just give me a second, okay? Just 5 seconds, and I'm gonna add time. I'm gonna back to you, okay? Here we go. So you saw in the previous case, guys, it was going here, but here at the end, remember, it was going crazy unstable. That's right. Yes, remember in the previous class? But now we added damper here. We added damper here, guys. Physical damper. And we made it to, what happened when we added physical damper? We gained the missed terms here, S cube and S. By doing that, we made system stable. Now you tell me, your system is underdamped. And I taught you, what do you expect to see as the poles of this system? As the poles. What kind of poles expect you to see for the underdamped system? Real poles, imaginary poles, complex conjugate poles, repeated poles, two distinct. Yes, complex conjugate, exactly. When you see underdamped, means that you have dominant, remember dominant poles? Yes? You expect to see a dominant pole for this system. This is fourth order system. Let me say it's a Sims X. Solve that for me. Solve what? Solve x4 plus 10 x cube, the denominator, that's right, plus 425 x squared plus 2000 in x plus 30,000. These are the poles of the systems, right? So then I'm gonna say these are the poles because I'm gonna share with you PL. Then I'm gonna say pretty double poles. Okay, let me double check. Yes. Now if I run this again, see, you have complex conjugate poles, guys, and all of them in the left hand side. You see, the real part is the same. It's interesting, but the imaginary part, they are different. It's a very interesting system, guys. Okay. So on the other hand, if you plot the poles, it has 4 poles. This system. if you plot that, real, imaginary. So here is minus 2.5. Oh, sorry, I have to delete this. So these are the poles of the system. Say here's minus 9, 2.5. Another is exactly the same real part, but minus 17 here. At the same real parts. Very interesting system. Okay. 1, 2, 3 pole. One of them is minus 9 point, plus 9 point I, minus 17 I plus. And the system behave like this. Okay? Understand everyone? Now you can kind of estimate in this fourth order system the amount of damping in the system. Guys, I'll give you 5 minutes that you look at this graph. Guys, how much is here? Let me magnify for you. This is how you do the modeling of the systems, okay? I should zoom in. Okay, guys. The value here is here exactly. This cross section is 6.7, say. Okay, 6.7. Understand? What's the overshoot of this system, guys? 6.7, and here is 8.74. So 6.7, 8.73. Yes, and equals to? Remember that overshoot of the system I told you for? Yeah, no, not percentage. See, MP, maximum overshoot I told you in percentage, is E minus zeta pi divided by 1 minus zeta square. So now you have this side. That's right. You have this side. So this side is 8.63 minus 6. What was the number I told you? What was the number I told you? 6.73. 73 divided by 100 equals to this. Now I give you 5 minutes that to calculate zeta from this equation. The damping ratio of this system. This is fourth order system, but you see acts as a second order system because it has a pair of complex conjugate poles. See what I'm saying, guys? Yes? Calculate that and let me know. Yes, 6.67. Guys, the number is 6.67. 6, 7. 8.63 minus 6.67. See, 8.73, yes. This is 73. Minus 6.67. Give me the answer. Take your time. Could you do it? Anyone? So please do it as homework. Okay, it's really simple. You have to just have the Neperian logarithm from the both sides, ln. Okay, and calculate minus zeta pi and this kind of things. Okay. That's it. So now, let me go back here. I told you, now you know you have 4 poles that has two pair of complex conjugate poles. Okay. So we calculated x1 over f1 here. Get here. x1 over f1. Okay. x1 over f1. Now if I say calculate x2 over f2, because you have from here x2 is here and you have x1, just replace it there, that's right. See what I'm saying? Just replace it there. Okay. But what if you want to go and do MATLAB things? Okay, by coding. Guys, look at these equations. Oh, these equations. I told you about the state variable and in the pendulum at the beginning of the class, right? By knowing that this is C, all of them, they are the numbers like that. And this is 2K, this is 2K, this is K, and K. I'm writing here all of them again, if you let me know. So what you're gonna have is M x double dot 1, now in time domain, plus C x dot 1 plus 2K x1 minus K x2 is equal to f1. M x double 2 plus again C. Actually, you know what? I can, okay, it doesn't problem. x2 plus 2K x2 minus K x3 is 0. We went for the Laplace domain. Now, when we see fourth order system, I want to see how to model in MATLAB by coding. Okay. What we're going to do that I'm teaching in the vibration course, but I'm going to hint here, you can write this in the matrix format. M0, 0, M x dot double 1. You had a question, sir. I'm sorry, I missed you. What was the question? The first one. So under this system, we have only one overshoot. Okay, this is the main overshoot here. Do you see? Okay, but the rest are being decreased based on the damped natural frequency. Okay, they are being decreased in damped natural frequency. What you say is the settling time. The settling time happens here. You see that here? Oh, it's here. This is settling time. Is 1 point, I don't know, 1.6 seconds. But overshoot is here, the main overshoot. And when it comes to the vibration class, the next one that is being decreased, and next one we are naming as the decaying log decrement, we name it, okay? But the overshoot is here, log decrement, okay? So, plus x dot 1 x dot 2 C0 0 C plus 2k minus k this is x2, this is x1, guys, minus k 2k x1 x2 f1 0. Now we define the vector of displacements. How? I say this bold capital, I'm gonna say is x1 and x2. So its time derivative x dot is x dot 1 x dot 2 and the x double dot gonna be x dot 2 x dot 1 x double dot. The name of this matrix in the control and the vibration is mass matrix M. The name of this is mass or inertia matrix. The name of this is damping matrix. Damping matrix. The name of this is a stiffness matrix. These are names. A stiffness matrix. We are showing with the capital K. We are showing with the capital C and M, capital M. So now you can write in the matrix format this fourth order system or fifth order system, 10th order system. 10th order system has 10 by 10 matrix, has 10 by 10 probability C and 10 by 10 stiffness matrix. So now you can said is M x double dot plus C x dot plus K X, and I'm changing as capital F, force is equal to F, and this is matrix vector, matrix vector, matrix vector, vector. Why we are doing that? Because I'm going to go transfer this into the MATLAB, this fourth order system. But before doing that in the next class, okay, I have to solve this. Let me do it. So guys, if I transfer everything, because these are the vector and matrix, okay, mx double dot equals to F minus C x dot minus K X. How to find x double dot from here, guys? I have to divide by m, that's right? Yes? Yes, everybody? Huh? Everybody agree? I have to divide by m, right? Yes or no? Everybody? Do I have to divide it? Hello? Disconnected? Guys? Cannot hear me? Okay. How to find x double dot from here? Yeah, exactly. Man, how we divide a matrix? You have to multiply by inverse matrix. inverse of that matrix. This is not number, this is matrix. Okay. What is this from high school or university level? Any matrix by its inverse. What? Identity matrix. So you have x double dot gonna be inverse of that matrix, mass matrix, in F minus C x dot minus a stiffness matrix X. I'm going to transfer this exactly in the MATLAB coding. Now, before I do that, you know that here gives you two state variables, remember? So M1 gonna be X1 and the M2, remember, in the pendulum, X dot 1. It's gonna be two state variables because your system is fourth order system. Guys, look at here. You're gonna have four state variables. If your system is sixth order, means that how many state variables you wanna have? 6 state variables. If your system is 20th order, it means that how many state variables you have? Huh? 20. So now M3, as we did for the pendulum, gonna be X2, and the M4 gonna be X dot 2. So if you remember, dm1 gonna be X dot 1, which is M2. dm2 gonna be X double dot 1. dm3 gonna be X dot 2, which is M4. And dm4 gonna be X double dot 2. Now the point is how to find this. Put here. Actually we did. Bingo. Because this is, look at here guys, X double dot 1, X double dot 2 equals to M inverse F minus C X dot minus K X. So if you want to find this and put here, you're gonna name this in the MATLAB coding. I'm gonna teach you like as A. So X dot 1 gonna be A, first column. X dot 2 that you're gonna put in the code gonna be A, second and first column. Here we go, second row, first column. And we're gonna introduce this in MATLAB one by one. Simple like that. Understand everyone? And you know that the X dot is what? You tell me. You tell me. X dot 1, X dot 2. Look at here. What is X dot 1? Guys. What is X dot 1? M2. What is X dot 2? M4. So you're gonna write here in MATLAB code M2 and M4. We're gonna do together. Your X is X1 and X2. What is X1? M1. What is X2? M3. You're gonna have M1, M3. Bingo. Everything is being based on that. We have M matrix number matrix, state variables. You can make your state space equations from it. We're gonna do that together next class. Okay? Okay, everybody? No, and when I give you the midterm, because I want you to focus on Thursday, we have no class. Okay, I'm gonna send email to everyone. Okay. Let me first